So as I mentioned, today is the last day we're covering new content this semester. Next semester we will start off with chapter 11 and we'll talk about free radical reactions, which go through very different mechanisms. And to finish off this semester though, we're going to finish off chapter 10, which is about alkynes. So last time on Tuesday we talked about the structures and some properties of alkynes, as well as how to name them, and the fact that terminal alkynes specifically are created where one side of the triple bond is bonded to a carbon group, or it could also be a hydrogen, but at least one side of the has a hydrogen, and that's that creates a situation where the pKa of this is low enough that there are a few strong bases, specifically the NH2 minus that we talked about, it comes with sodium counterion, is strong to pick up that proton and get a negative charge on a carbon. And we're going to see this a lot more in the reactions we discuss next semester, but creating a negative charge on a carbon is excellent. We know that that's difficult to do because carbon isn't normally stable with a negative, and in this particular instance, it's more stable due to the more compact sp orbital that holds the electron pair relatively close to the nucleus. But there are other examples of somewhat stable negatively charged carbons. In any one of those instances where it can put a lone pair on a carbon and have it actually sit there for most of the molecules is great, because that allows the substance to act as a nucleophile, and if I can get it to attack another carbon with a leaving group, I can start to imagine how to create new carbon-carbon bonds, which is really valuable. We've seen a few different structures this semester that are natural products or pharmaceuticals, and what you may have recalled seeing for those is most of those important organic compounds that actually have value have really pretty complicated carbon skeletons. And so if we want to make those compounds, we have to start with simpler molecules with fewer carbons and build up the complexity of the structure, and that often involves forming new carbon-carbon bonds. So this is the first example we've seen this semester, and there'll be many more next semester, where new carbon-carbon bonds can form. We're going to finish off the semester talking about that. But first we want to talk a little bit about how to make alkynes. So we know if we have a terminal alkyne, we can make it into a nucleophile, but how do we make alkynes in general? And so the only way that you have to know to make alkynes for this semester is through an elimination reaction. So if you start with one leaving group and one beta proton and use a strong base like H minus, the DBN, or the DBU we talked about, or an oxygen, as long as it's sterically hindered enough, I don't have to worry about the oxygen coming in as a nucleophile. It could potentially come in as a base, proton, and push out the leaving group. We also now know NH2 is a great base, so that's also an option. So we have a variety of different options. Some of these are much less sterically hindered, like the NH2 and the H minus, and so they can access beta protons more readily. They're also pretty strong because they're quite unstable with negative charges. The negative charge on the oxygen is a little bit more stable, but still pretty unstable due to its small size. So we would expect any one of these bases to do an elimination. We talked about that way back when, seems like a while ago now. And we can make an alkene if we have one leaving group and one beta proton. So to make an alkyne, we just do the same reaction, but we just need two leaving groups and two beta protons. So in this case, we would need at least 2 moles. So we could use excess of the base. We'd need 2 or more moles of the base so that one mole would pick up a beta proton and push out whichever leaving group is anti-periplanar to it. And then another molecule kick off the other beta proton, push electrons in and push out the leaving group that's anti-periplanar to it. And that will introduce two new pi bonds into the space between where those groups were eliminated. So this is an elimination reaction. It's an E2. Assuming we're using strong base, it starts the process off. You don't have to worry about forming any unstable carbocations. And that's probably the main way you want to think about trying to make alkynes. So the example we just looked at, the two leaving groups are on the same carbon. And that relationship when two atoms or groups are on the same carbon is called geminal. So a geminal dihalide has two halides on the same carbon. And we just saw how that could work. One proton's picked off to make the alkene, and then the second proton, as long as it's anti-periplanar to the leaving group, can be picked off to make the alkyne. So that works as an option to start with a geminal dihalide. We could also start with a vicinal dihalide. The term vicinal means that they're on adjacent carbons rather than on the same carbon. So here, my strong base would pick off one, and push that bromine out, and then another molecule of the strong base would pick up the other proton and push the other bromine out. So they still have to be anti-periplanar because it's E2, but as long as that setup works, I can create an alkyne from that as well. So geminal or vicinal dihalides are the options there, and that's really the background you needed to answer the first question on the quiz questions today. So if I want to make one pentyne, that would have 5 carbons, 1, 2, 3, 4, and then to draw the structure for that, the 5th carbon, the 4th carbon, and the 5th carbon are both linear because they're sp hybridized. So I'd want to represent that when I show the structure. So working backwards to make that, there are really two different options. I could use a vicinal dihalide or a geminal dihalide, meaning I could put the two halides on the same carbon. Oops, make that a bromine. And as long as there are two hydrogens here, and this single bond can rotate, there's every reason to think that it would rotate until one of the bromines is anti to one of the hydrogens, so that can be eliminated to make an alkene. And then if that occurs in such a way where the other hydrogen still ends up anti-periplanar to the other bromine, once the alkene's formed, it can no longer rotate. But after the alkene forms, as long as the remaining bromine is anti to the remaining hydrogen, the second elimination can occur there and you get the alkyne. So if I use the two bromines on the same carbon, I'd want them to be on the end. I probably wouldn't want to start with them both here, because then I run the risk of these other alpha hydrogens being removed and forming the triple bond in the wrong position to make 2 pentyne instead of 1 pentyne. So that would be one option. Alternatively, you could put the halides on adjacent carbons. I'd still want one on the end, and then I'd want one here. So this hydrogen would be anti to this bromide, and then the other bromide would have to rotate to a position where it's anti to this hydrogen. And then I could still do the elimination and get the triple bond in the correct position. So either of these options would potentially work. So that's why there are two sets of reagents. So in either case, in terms of my reagents, I definitely need a strong base. So an H2 minus would work, an H minus would work. Oops. Any of the strong acids that we talked about, or strong bases that we talked about to promote E2 elimination would work there. If this reaction were to occur to create 1 pentyne, maybe this R group is a butyl propyl group, so I have 5 total carbons. or really any other carbon group, if I put my two bromines on the end, do the reaction we just talked about, picking off a proton, eliminating the anti-periplanar leaving group, pick off the other proton with the second molecule of the base, eliminate the other leaving group, create the alkyne. If I do use a base as strong as this one, as soon as the alkyne is formed, any remaining NH2 will act as the base and deprotonate it. So that's why I get this negative charge. So if I'm trying to create this so it can act as a nucleophile, and I want that to attack some electrophile, like maybe an ethyl bromide or something, I want that to come in here and do an SN2, that's great. I can kind of kill two birds with one stone, so to speak, or in other words, one reagent, just using an excess of it, more than 2 moles, 3 moles total of that reagent, can go all the way from the dihalide to the nucleophile. If, however, I want to stop at the alkyne and I don't want it to further react and maybe act as a nucleophile, then in a second step, which would, the first step would go all the way to this compound here. In a second step, I would just add water, because water has a low enough pKa that it would quantitatively donate protons and convert the deprotonated alkyne back into the terminal alkyne with the proton situated there. So because the NH2 is such a strong base, these equilibria pretty much go all the way to the negatively charged carbon due to its compact sp orbital versus the more elongated sp3 orbital in the negatively charged nitrogen. So if I want to then get back to the actual alkyne rather than the deprotonated alkyne, water would be a great molecule to use. It's obviously super cheap and abundant, and its pKa is low enough compared to the pKa of the alkyne that this equilibrium pretty much quantitatively favors the product side. So if you see those two sets of reagents in sequence, that's what's happening. The first set of reagents is doing the elimination and deprotonating the alkyne. So that first set of reagents would give me that compound, and the purpose of the water in the second step is to protonate that and make the terminal alkyne, or neutralize its charge. These have to be added in 2 separate steps. They cannot be added all together. If I add it all together, then the NH2 will simply react directly with water by deprotonating it. And that will convert all my strong base into a less strong OH minus, which might do the same elimination, but it might also act as a nucleophile. And so, I'm adding these reagents. I don't want them reacting with one another. I want them reacting with my substrate. So that's why I have to add them in second step and 2 separate steps. All right, so that's going to be how you make an alkyne. So if I ever give you a question where you're trying to make an alkyne, you have to first create some kind of dihalide and then do this elimination, and you'll have the alkyne. Once you produce the alkyne, there are a variety of reactions that they can undergo, which you want to be familiar with. So most of these reactions are addition reactions, similar to an alkene. The pi electrons are not held closely to the nuclei. An alkyne just has 2 pairs of pi electrons. So they're even more susceptible in general to reacting with addition reactions. Right? So if I can convert one of these pi bonds into a sigma bond, I'd have to break these here. So I'm breaking a pi bond and a sigma bond, form 2 sigma bonds. The sigma bonds are more stable. And so if that happens once, why not do it again? Break the other pi bond and create 2 more sigma bonds. So I'd have to break 2 sigma bonds here, 2 pi bonds. I get to form 4 new sigma bonds. That should be favored. So in general, most of the addition reactions we talked about in chapter 9, where we're converting alkenes pi bonds into sigma bonds, can also be used on alkynes. So we're just going to look at those reactions here and talk about some of the ways that they're a little bit different when we're reacting addition reactions across an alkyne pi bond versus an alkene. When it comes to hydrogenation, if you use the standard hydrogen and metal catalyst that we've been talking about using in hydrogenation in chapter 9, that will add hydrogens across a pi bond if it's an alkene. It'll add hydrogens across both pi bonds if it's an alkyne. So if you add hydrogen and it adds across here, it is going to add to the same side. So it will initially create the cis alkene, where the 2 hydrogens are on the same side of the pi bond, right? Because they're added at the same time. The metal catalyst allows this mechanism to happen more readily than it would otherwise happen, but it still creates a situation where the pi bond and the hydrogens approach one another on the same side. So the pi bond sits down on the surface of the metal, the hydrogens are there on the surface of the metal, they both get added to the same side, and so that's why I get cis. Once this alkene is produced, I can't control whether a molecule of hydrogen, then the next molecule of hydrogen, goes on to react with the alkyne and produce more alkene, or maybe it will react with the alkene and convert that down to the alkane. So since I cannot control, once a little bit of alkene is produced as the alkyne addition reaction produces it, I can't control whether that is the next thing to react or whether the alkyne reacts, just based on where the molecules happen to collide, which particles collide when. There's no way to control this reaction and prevent a full hydrogenation from occurring. So the only time you would use H2 metal with an alkyne is if you wanted to convert it all the way down to the alkane and fully saturate both of the pi bonds. So if that's the reaction you want to perform, that's the way to do that. There is a way, though, to convert the alkyne into the alkene without fully hydrogenating it to the alkane. And so that's what we also want to talk about. There are 2 ways to do that. One gives you cis, the other gives you trans. So normally, if we use H2 and platinum or palladium or nickel, one of those metals in powder form with hydrogen gas, I would need 2 moles of this, but that would go all the way to the alkane. So make sure you're aware, hydrogen with any straight metal catalyst is going to go all the way from the alkyne to the alkane. If I want to stop at the alkene, I need a different catalyst. And so researchers, including some person named Lindlar, came up with some alternative catalysts that still do involve a metal. We're not going to get into the details of how this works, but this combination of substances will catalyze the first addition of hydrogens across the pi bond, and since they add to the same side, I get a cis alkene. But this alkene doesn't interact effectively with the catalyst to allow another molecule of hydrogen to add across there and give the alkane, so I don't see that second part. So if you have an alkyne and you want to convert it into a cis alkene, all you have to do is write Lindlar catalyst over the arrow. You don't need to know the specific substances involved. As long as you know that it's a Lindlar catalyst or the so-called, you could just write poison catalyst. That's enough to indicate that you understand that those catalysts exist And if you needed to find out exactly how to use them, you could Google that and find some article that describes that procedure or experimental method. So as we were saying, with the Lindlar catalyst, the poison catalyst, it facilitates the addition of the hydrogen across the alkyne pi bond, so that is catalyzed and happens fairly often, but it doesn't catalyze the addition of hydrogens across the alkene pi bond. And so the next step goes basically with the same energy it would go with if I didn't have the catalyst at all. And so that means kinetically, right? So the reason this stops at the alkene and doesn't go all the way to the alkyne is not thermodynamics. Thermodynamics would predict, if these are all in equilibrium, that the equilibrium would eventually produce the substance that's got the lowest free energy, the substance that's most stable or has the most entropy. And due to all the extra sigma bonds over here versus pi, this one should at least be definitely lower in enthalpy and probably for that reason lower in free energy and thus favored thermodynamically. So if you allowed an infinite amount of time to go by, eventually all the molecules would be converted to alkane. But what we're doing here with the catalyst is taking advantage of the kinetics, where if we're able to speed up the first conversion from the alkyne to the alkene, but we don't also speed up the second conversion, well then this reaction can happen and establish equilibrium, which would favor the lower free energy alkene versus the alkyne. But if we don't have the time and energy available to get over the second transition state, then all the molecules would accumulate in this form, and I can create the cis alkene with a reasonably high yield without having to worry about much of it converting into the alkane. And so this is syn addition because the hydrogens are adding to the same side of the double bond. Right? So I should not get any of the trans alkene when I use the Lindlar catalyst, because this catalyst does not facilitate the hydrogens adding on opposite sides of the pi bond. If I do want the trans alkene, I need a different set of reaction conditions. So I'm not using hydrogen gas here. The H2 always, on the surface of the metal, the two hydrogens always add to the same side of a pi bond. So that either converts an alkyne into a cis alkene, or if I'm not using the poison catalyst and I'm just instead using a standard palladium or platinum or nickel catalyst, it still adds the hydrogens to the same side, so I'd still be getting a syn addition. In that case, the single bond would immediately rotate to avoid eclipsing and torsional strain, but the hydrogens are still adding to the same side of the pi bond. So I'm still getting syn addition anytime I use H2, whichever catalyst is present. So if I want anti-addition, so we're not talking about anti-Markovnikov here, we're just talking about anti in the stereochemical meaning, where the two hydrogens are added to opposite sides, I need a totally different mechanism. I'm not going to use H2. I'm going to use a metal that has a free electron that it's desperate to get rid of. So sodium works here, or you may also see lithium. But it's not sodium or lithium ions. I'm not dealing with an already stable sodium or lithium that already has a full positive, because that would have a noble gas configuration and be stable. It wouldn't react. It already has a noble gas configuration. That's not what we're looking for in this reaction. We're looking for a metal atom that is desperate to get rid of an electron so that it can make its noble gas configuration. And so this pi system is going to be forced to pick up that electron. And so we're going to look at the mechanism for that. That is a mechanism I may expect you to be able to draw on your exam the week after Thanksgiving, which is when you'll be tested on this content. So let's take a look at that reaction. One thing we do know before we do, though, is that water cannot be used as the solvent in this reaction, because if sodium or lithium exists in the presence of water, there will be a direct reaction between the two. If I want the lithium or sodium to react with the alkyne, I can't provide a solvent that would instead react with, right? If this happens, the lithium will give, or sodium will give an electron over to the water. Well, how can water take on a new electron? It already has 8 around the oxygen, making its noble gas configuration. Well, first of all, when we're using curved arrows to show electron movement, normally we use an arrow, normal arrow, and that shows the movement of 2 electrons. If I only have 1 electron moving, then we use this fish hook shaped arrow, or like the arrow doesn't have a full head, it only has half a head. That indicates only 1 electron is moving. So if this electron comes over here to the oxygen, this OH bond would have to break. 1 electron would stay with the oxygen, and the other electron would go on the hydrogen. And so that would allow the sodium to lose that electron. It would now be without it, which is good because that completes its noble gas configuration. The oxygen would then have that new electron from the sodium, in addition to the 2 lone pairs it already had. And one of these electrons from the OH bond also comes over there and joins up with this. So that gives me an OH minus, which isn't extremely stable, but at least the oxygen has a noble gas configuration. The hydrogen takes the other electron. And so you're probably wondering, well, how is that helping? If the sodium had the electron and didn't have a noble gas configuration, and now the hydrogen has an electron, doesn't have a noble gas configuration, that's not any more stable, which is true. So what would happen is, this would happen twice. And when I have 2 hydrogens that each have a single electron, those electrons will simply join together to produce hydrogen gas. So that way, all the molecules involved can make complete noble gas configurations, and that's what drives that reaction forward. So you can't have sodium or lithium in water. They'll react to produce hydroxide, hydrogen gas, and sodium or lithium ions. So in this reaction, we need the sodium or lithium to be in a solvent they won't react with. Ammonia, though, is normally a gas at room temperature, so we need to cool this way down below the boiling point of ammonia so that it'll actually be in the liquid form, and it'll be able to mix and dissolve everything and facilitate the collisions in the liquid state. Right, so there's some caveats in this reaction that we want to be aware of. All right, so here's the mechanism. So the alkyne, as we said, is going to accept the electron from the sodium or lithium. And when the sodium or lithium loses the electron, it's going to join up with one from the pi bond, and the other from the pi bond is going to split over here. And this creates a really unstable intermediate. I've got a full negative charge on a carbon, and I have another carbon that only has 2, 4, 6, 7 electrons. It doesn't have a complete noble gas configuration. So I've got 2 adjacent carbons that are really quite unstable. And so this intermediate is pretty unstable. It's not going to exist for very long. The sodium gives up electron to make its noble gas configuration. So that's really what drives this process forward. That electron is just not held tightly at all by the sodium's nucleus. So when they collide, the carbon attracts it better than the sodium because it has less shielding. It can move it into its second energy level. But this is also a really unstable intermediate, so this intermediate is going to react further. The intermediate that's formed, let's take a look at it before we look at how it's reacting. We could imagine it forming in 2 different stereochemical or spatial arrangements. And so what we see is, due to these R groups probably being sterically hindering, they avoid proximity where they might repel. And the electron clouds here that holds the lone pair that's negatively charged, and this electron, even though it doesn't create a negative charge, it's still a cloud with an electron, they repel as well, if they get too close together. So in this first step is what determines why we get anti-addition. When the electron comes in and this bond splits up, the two R groups are going to end up on opposite sides instead of on the same side to avoid both of these areas of repulsion. So we form this so-called radical anion. It's a radical because it has an electron that's not paired up with another electron, and it's an anion because it has a negative charge. And we're going to form it in the trans configuration, where the R groups are opposite and the electron clouds are opposite. But as we said, it's really still quite unstable. So the next reaction that it's going to undergo is to pick up a proton. A carbon with a negative charge is almost always less stable than a nitrogen with a negative charge. So when this carbon picks that proton up and the nitrogen keeps these electrons here, the nitrogen will take on a negative. The nitrogen has the electron pair and an sp3 orbital, versus over here, this is an sp2 orbital. So we did say when a carbon has a triple bond and it has a lone pair and an sp orbital, that negative is stabilized by the compact shape of the orbital more than a lone pair would be stabilized on a nitrogen in a more elongated orbital, even though the nitrogen has one proton more than the carbon to more strongly attract the electron. Right, so that was our exception where the orbital was more important than the atom carrying the charge. But in this case, the orbital difference between sp2 and sp3 is not big enough. So a negative on a carbon, due to the atom having fewer protons and not being able to stabilize the negative as effectively, even if it's in a slightly more compact sp2 orbital, is not as stable as a negative on a nitrogen because the nitrogen has an additional proton. So this step is definitely going to be product favored, to put the proton on the carbon instead of on the nitrogen. The nitrogen will form a negative, and then what will happen is this free radical will pick up another electron from another sodium atom. And so far we used two sodium atoms, one to donate the first electron so that that atom can make its noble gas configuration once the electron's gone, and then that happens again to make another sodium with a noble gas configuration. So then after that electron gets picked up, then I simply have a lone pair here instead of a free radical. So that completes the noble gas configuration for this carbon. Right here, as we said, the carbon only has 7 valence electrons. Here it has 8. So it's more stable in one way than now that it has a complete noble gas configuration, but it's also less stable in another way in that it's got a formal negative charge. So that is going to do the same reaction we saw here. It's going to do a proton transfer where that formal negative picks up another proton, and that produces the trans alkene. And in this case, we do not have to worry about that reacting further. And the reason for that is because the first step of this mechanism, it won't work so well on an alkene as it would on an alkyne. So if I imagine my alkene, and I imagine a sodium atom trying to donate an electron to it through the same mechanism, the electron will go over here, this pi bond would split, and that would produce something like this. There'd be a couple hydrogens here now. This carbon would have 2 electrons because there's one from the pi bond coming over and one from the sodium coming over. And this cloud would have 1 electron. So the difference is now these carbons are, well, at least this one is sp3. And so the negative charge is way less stable due to the more elongated orbital than it would be in an sp2 orbital. Right, so that's really the beauty of this reaction. If you want to take an alkyne and convert it into an alkene that's trans by adding two hydrogens across. This mechanism will do that, as we showed. And then the alkene that's formed won't react further with the sodium because it would produce an even more unstable transition state and intermediate here with a negative charge in an sp3 orbital. So we don't have to worry about that reacting further. We don't need a poison catalyst or anything like that. This reaction and this mechanism would stop at the trans alkene. So what about the pKa values in this step? Well, if you remember, the pKa value for this proton is around 45, I believe. The pKa value for this proton is around 38. So even though this is an extremely weak acid, its pKa is still lower than the alkene, and so the equilibrium here should definitely favor the side with the weaker acid or the higher pKa, and it would do so by 45 minus 38, which is 7 pKa unit difference, which means the products would be favored by about 10 to the 7th. So that's a very product favored equilibrium, and so that's the result of solvent, and it's acting as an acid. It's a very weak acid, but still stronger than the product, so it still drive that equilibrium toward the desired product side. Any questions about any of that? So we can apply this reaction to some molecules. If I have an alkyne and I go through the mechanism we just discussed using these conditions, make sure you understand the difference between sodium and NH3 versus NaH2. Very different reactants. Na, without any charge shown and without any other elements involved with it in a compound, it's just a single atom, an element. If there's no charge shown, it's assumed to have an electron, which is what we need to get this process started. We just showed the mechanism. NaNH2, when I have a sodium combined with other elements, it's assumed that the sodium has a noble gas configuration and that the remaining part of that would have a negative charge due to the lone pairs on the nitrogen. All right, so this is a strong base. This set of conditions is not a strong base. It promotes the free radical mechanism we just saw because of the extra electron the sodium has to give away. So be very careful about whether you're using a neutral sodium that can donate an electron to do the reaction we just talked about, or whether you have a positively charged sodium that already has a noble gas configuration, is just a spectator ion. So with this set of conditions, that would convert my alkyne, I'm going to count the carbons here, make sure I don't make any mistakes, into a 6-carbon chain, 2, 4, 6 that has a trans alkene. So I would go from 3-hexyne to 3-hexene. And that would be trans 3-hexene or E3-hexene. We'll do the same thing here. So here I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 carbons. And I'm going to add the hydrogens across that double bond. I'm going to do so in a trans fashion through the mechanism we just talked about. Oops. So let's count these off. So there we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, I got too many carbons there. Ignore that one. Let's connect these two. But if I show the bond between 1 and 11 like this, then it looks like it's a cis. So I didn't do that right. I need the hydrogens to be on opposite sides because of the way this mechanism produces the electron clouds on opposite sides. So I'll have to redraw that one. So I want to make sure that the bond between 1 and 11 is trans. So then I can go 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. And obviously your bond angles don't have to be perfect. It's difficult to draw big rings like that and get the bond angles correct. As long as you show that the double bond created is trans and you still have the correct number of carbons, you're good in that situation. So here's a summary of what we just talked about with an alkyne. If you want to do hydrogenation of an alkyne, there are 3 ways to do it. If you use the conditions we talked about for hydrogenation, you'll hydrogenate both pi bonds and you'll add 2 sets of hydrogens across at both pi bonds. And so really you would need excess of that, or at least 2 moles of it. And in reality, when you do these experiments anyway, you're almost always using a large excess of hydrogen because you need a high pressure of that to create lots of collisions to force the hydrogen to collide with the platinum, and then the platinum helps deliver those hydrogens across the alkene. If you don't want to go all the way to the alkane and use the Poisson catalyst, that will add the hydrogens in a syn addition and stop at the alkene. If you want to go further, you can then add hydrogen after that, which would be silly because if you're going to do that, you might as well just do it from the start. So the Lindlar catalyst is used if you want to stop at the alkene that's cis. And the reaction conditions we just talked about, where I'm using sodium, neutral sodium, and NH3 as both my solvent and my weak acid, that would stop at the trans alkyne or alkene. I could then further hydrogenate that to the alkane, but if I want to stop at the trans alkene, this is the set of conditions to do that. And that basically answers the next quiz question. If I want to make cis-2-pentene from an addition reaction, I just draw cis-2-pentene. 1, 2, 3, 4, 5. It'd be cis if the 2 hydrogens here are on the same side of the double bond. If I want to make that from an addition reaction, I'd have to start with 2-pentyne. 1, 2, 3, 4, 5. And that would add H2 and the Lindlar catalyst. That gives me the cis addition. If I want to make trans 2-pentene, I would start from the same reactant, but I would use sodium or lithium and then H3. And that would give me trans 2-pentene. Alright, so that's hydrogenation of alkynes. There's 3 ways to do it. We also talked about hydrohalogenation. Hydrohalogenation of alkenes undergoes a Marconic addition. Where if I have an alkene and I add a hydrohalogenation, that's a hydrogen and a halogen, the hydrogen adds to the side that already had more hydrogens, and the halogen adds to the side that had fewer hydrogens to begin with. Right, that's a Marconic addition. It goes through a carbocation intermediate. Well, it turns out I can use HBr to also react alkynes, not just alkenes. Right, so I get the Marconic addition HBr or HCl, where the Br or Cl comes into the carbon that's more substituted with carbons, because that's where the carbocation forms in the intermediate, as the pi bond starts off by picking up a proton and adding that proton to position where there are already more protons to create the more stable carbocation. Then X comes in to connect to where that carbocation was. We can do the same reaction with an alkyne, but the mechanism is different. There may actually be some controversy about this mechanism. So let's look at this in a little bit of detail here. We still get Markovnikov addition. We still get the hydrogen adding to the carbon that already had more hydrogens, and the halogen goes to the other carbon. If you add 2 moles of HX, the second one would also go through a Markovnikov addition. So once I have an alkene, the mechanism would be the same as what we've been looking at, where I first form a carbocation, and in this case, so the end carbon would pick up the proton, forming a carbocation here, so it would be secondary, but also would have either a chlorine or a bromine from the first HX reaction present there. And while that destabilizes the carbocation through induction by withdrawing electrons, it also stabilizes it through resonance by donating a pair of electrons. So that helps to direct the second addition reaction here to also be a Markovnikov, because the carbocation that forms will be stabilized through resonance, and that will attract the other X into the same atom. So that's going to give me a structure that looks like this, with 2 X's on the same carbon. 2 bromides or chlorides there. So I can do the Markovnikov addition, and then if I use excess of the HBr or HCl, I can do another Markovnikov addition and get a dihalide there. Once I have the alkene, it goes through the mechanism we already talked about. So let's look at a little bit more detail of the alkyne forming into the alkene. We could imagine the same mechanism, which would involve a proton transfer, forming a carbocation, and then a nucleophilic attack to give me the Markovnikov product. Problem with that is threefold. One is the reaction rate is very slow. And that's because it's third order overall rate law. And this is the biggest issue with this mechanism. If this mechanism were correct, if I have one molecule of this colliding with one molecule of this in the slow step, that would require, or that would end up creating a situation where the rate would be equal to the rate constant times the concentration of one reactant times the concentration of the other reactant. If one of each is involved in the collision, then doubling the molarity of either would double the rate. And that would mean that they're both first order, which would give second order overall kinetics. But when you experimentally look at this, it ends up being third order overall kinetics. So that disconfirms this mechanism. This mechanism cannot be correct because the mechanism would give second order overall, but what we see experimentally is third order overall. Another reason this mechanism isn't likely is that it goes through a vinyl carbocation. And what we said is vinyl carbocations are similar to primary carbocations in that they're they're even more unstable than primary carbocations, because this is an empty sp2 orbital. A compact orbital relatively close to the nucleus is very difficult to create an empty orbital there because it really strongly attracts electrons in. It's very unstable to not have electrons in a space that's close to the nucleus. So we wouldn't even expect this to form, and the fact that the experimental kinetics don't match the kinetics for this mechanism as well really disconfirmed that it's going through the same mechanism that it would go through if we were adding HBr, HCl across a double bond instead of a triple bond. So there's some speculation about this mechanism. If you look at the experimental rate law, you find that it's first order with respect to the alkyne, but second order with respect to HX. So that may suggest that two HX molecules have to collide with at the same time here. So maybe one of these HX molecules reacts, and at the same time maybe another HX molecules reacting. So it might require two of these to collide with one of these. If all three of those have to be involved in the collision to make the product, well then the HX would be second order, because if I double the molarity of those, I'm going to really help facilitate these collisions. And if I decrease the molarity, almost never will these collisions occur, because the collisions specifically require 2 moles of that. The more moles there are involved in the collision, the more the molarity of that will affect the rate. And so it becomes an exponential relationship instead of a proportional relationship. So that could explain the rate law, but there's still some confusion. So this type of collision would be called termolecular, where 3 individual chemical units have to collide at one time. The odds of that aren't very good, so it leads to a very slow process. So that matches with the experimentally determined rate law and the slow kinetics, but it's not really fully accepted as the correct mechanism. So I just wanted to point that out as a little bit of interest there. So here's kind of how this mechanism could look. There may be other competing mechanisms involved here, but if you're asked about this, you would want to mention, in order to be consistent with the rate law, the best mechanism we can probably come up with is that 2 molecules of HX are involved, and they both have to collide with the alkyne at the same time, creating this transition state where the pi bond is breaking, a new bond to a hydrogen is forming, and a new bond to a halide is forming, all at the same time. And so since that involves 2 molecules of HX, it would be second order with respect to HX. We're not going to get into that mechanism too strongly because it's not really totally accepted as it is. We can also do an anti-Markovnikov hydrohalogenation. And again, we're not going to get through the mechanism for that until next semester. So whether I'm doing an anti-Markovnikov hydrohalogenation of an alkene or of an alkyne, it's basically the same reaction. So without the mechanism, we're not going to explain how or why it works, but if you add peroxides in HBr, you get the opposite regiochemical outcome if you didn't have them, right? So we just showed if I just add HBr with no peroxides, the H adds to the Markovnikov position where there are already more hydrogens. So I get this product here. I get an extra hydrogen on the end, and I get my bromine there. That's the Markovnikov predicted product. If I put peroxides in the reaction, it totally changes the mechanism. I go through an entirely different mechanism. Well, we have talked about that. We're not going to discuss it until next semester. What you should know, though, is that I get the opposite regiochemical outcome where the hydrogen ends up going to the carbon that didn't begin with more hydrogens, and the Br ends up going to the other carbon. And that creates a situation now where I have 2 different stereochemical outcomes. I can get the 2 top priority groups on opposite sides of the pi bond, which would be Z, or I can get the 2 top priority groups on the same side of the pi bond, which would be, this is E, which would be Z. This one would also be trans, because I have 2 identical groups on opposite sides of the pi bond. This one will be cis because I have 2 identical groups on the same side of the pi bond. They'd also be E and Z in this case. So that's a problem. It's not ideal to have a mixture of products formed. If I'm only trying to produce one of them, then I have to get rid of the other one. That's a whole issue experimentally. So there are limitations here synthetically, but this would be the outcome if you reacted an alkyne, terminal alkyne with HBr with peroxides. A couple other reactions. For an alkyne, we talked about hydration of alkenes, and we said we can use an acid and water. And in this case, the mercury sulfate additive helps to catalyze the reaction. So what happens here is the mercury will attract one of these pi bonds. And we've seen something like that before through the ring with mercury. That will help water attack. So we can't just use standard acid, because if I just use H3O+, which would come from sulfuric acid reacting with water, and I imagine that picking up a proton, if that picks up a proton, it will pick it up on the end here, and then I would get a carbocation. The carbocation is vinyl, and we said that's really unstable. It's really prohibitively unstable. So we can't go through the same mechanism we did earlier when we did a hydration of an alkene. We showed hydration of an alkene gives Markovnikov addition, it goes through a carbocation intermediate. Hydration of an alkyne, the carbocation intermediate is too unstable. People are not hearing me? Alright, let me try to re-establish the feed. Can people hear me now? I didn't mute myself. I think there may have just been an error with Discord. Anyone hear me now? Oh, apparently not. Try that again. Okay, can anyone hear me now? Okay, good. Thank you for messaging in there. That was just a glitch, I think, with Discord. I had to exit out and restart the program there, so we should be back on track now, hopefully. So I'm not exactly sure where I cut out. What I was saying was, if we react H3O+ with an alkene, we saw this previously, the alkene can pick up a proton. Oh, dang it, you're right. I gotta share my screen again. Keep forgetting that every time there's technical problems. Alright, jump back on. Thank you. I appreciate you all helping me out with that. Make sure everything gets fixed when there's a problem. Okay, so I was saying that the alkene can react with H3O+ because when it picks up a proton, the proton can add to the Markovnikov predicted position and leave behind a carbocation. But with an alkyne, if the alkyne picks up a proton and does the same thing, to form a carbocation, it would form on a carbon that's vinyl. And that would mean an empty sp2 orbital, which is much more compact and unstable than an empty p orbital, because the p orbital is more elongated. So the carbon can afford to have space so far out be empty, but the space closer to the nucleus, if that's empty, then that's really unstable. So the point of the mercury is to help bridge that. So when the pi bond picks up a proton from the acid, instead of forming a carbocation here, this wouldn't be here, the mercury would first destabilize that, and then instead of forming a carbocation here, it would only be a partial positive because the mercury would be coordinating there, sharing some electrons and taking on some of that positive charge. It still would, though, allow the water to come in as a nucleophile and end up in the Markovnikov predicted position. So after the water comes in, this position here, I can hear someone typing, FYI, so if that's you, please make sure you're muted so you don't say anything embarrassing. Then another water would deprotonate this, and that would produce what's called an enol. An enol, the word enol refers to an alkene and an alcohol. So the alcohol is the OH, the alkene is C double bond. So when I have an OH directly bonded at the vinyl position of a CC double bond, that's an enol. And when an enol forms, the CC double bond is not as stable as the CO double bond. So that undergoes an equilibrium where it rearranges to form a more stable compound called a ketone. So ultimately what's happening here is I'm converting an alkyne into a ketone. A carbon-carbon triple bond converted into a carbon-oxygen double bond. And these compounds are very common. It's a very common functional group. You might be in a situation where you want to make a molecule that has this functional group. And so starting from an alkyne and using these conditions, going through the enol intermediate can be a convenient way to do that. So let's take a look at this last part here where the enol converts into the ketone. So we talked about the reason it's called enol. It has an alkene and it has an alcohol directly connected. So what happens here is the reaction has H3O plus generated by sulfuric acid reacting with water. So the enol picks up a proton from the H3O plus to form this carbocation that's stabilized through resonance. And then a water molecule picks off this proton and I have a ketone. And so that equilibrium can shift back and forth. These two compounds are called tautomers because they're interconverting constitutional isomers. It's obviously different from resonance. Right? These two structures are not in resonance with one another because they're not just, the difference is not just shifting electrons, and it's not like there's an extended electron cloud that exists over the whole thing. I actually have to disconnect hydrogens and reconnect hydrogens to get from one to the other. So I have to do proton transfers. That's equilibrium, not resonance, right? So I'm looking at the stability of the CO double bond being more stable than the CC double bond. That's what drives this equilibrium toward the product side, and that's why it's very difficult to isolate an enol. Even if you want to make the structure, as soon as you make it, if there's any tiny amount of acid or base catalyst around, it will pretty quickly convert almost exclusively into the more stable CO double bond form. So that's what we end up with. If we want to convert an alkyne into a ketone, these are the conditions. So you want to at least know enough about the mechanism or memorize this set of reagents so you can predict correctly what the product would be in those reactions. So that's what happens if I do a Markovnikov hydration of an alkyne. I end up getting an enol, which converts into a ketone. If I do an anti-Markovnikov hydration of an alkyne, I get the opposite regiochemical outcome. Right? So we know with this borane reagent, the boron adds to the side that's less sterically hindered, and the hydrogen adds to the carbon that's more sterically hindered. Because hydrogen is smaller and the BH2 is a little bit bigger, it's going to go to the less hindered side. And in addition, the electronegativity difference here means the boron takes on a partial positive. So the pi electron attracted to it, being pulled away from the carbon that can stabilize the positive a little bit better, but then that immediately draws the pair of electrons from the hydrogen in there. So initially what's going to happen here is the hydrogen will add here, and the boron will add here on the same side as the hydrogen. And then, as we talked about this reaction previously, the second set of conditions replace the BH2 with an OH. So I do anti-Markovnikov, right? The hydrogen, there's already a hydrogen here. The second hydrogen that's added is not going to add to the carbon that already had more hydrogen, so it's not Markovnikov. The second hydrogen is going to add to the other carbon here, and that's why it's anti-Markovnikov. But it still produces an enol. So the enol is going to undergo tautomerization again to form the CO double bond, which is more stable than the CC double bond. In this case, though, the mechanism will be a little bit different because instead of being under acidic conditions, we have an OH, which means we're under basic condition. So what's going to happen here is the OH minus is going to react with the enol, first to deprotonate the OH, and then the negative charge that sits here will be stabilized through resonance, right? So it can exist spread out between the oxygen and the carbon. And then if that carbon picks up a proton, I get the CO double bond. Right, so obviously these two structures are the most stable structures in this equilibrium because they don't have any formal charge. But the CO double bond is definitely more stable than the CC double bond. That's something you want to think about a little bit. The reason for that is nothing we're going to get into. That's more something you just have to kind of remember. And next semester we'll do a lot more examples that will help you remember that. But when you have the alkyne and you do anti-Markovnikov addition, the OH adds to the hydrogen, the carbon that already had more hydrogen. And then once the tautomerization occurs, the double bond ends up there, and you get something called an aldehyde. Right, so if I have a CO double bond that has two carbon groups, that's a ketone. If one of those is a hydrogen, and the other is either a hydrogen or a carbon group, that's when I get an aldehyde. So a couple issues with this reaction. Right, we talked about why the boron and hydrogen add across the pi bond in the regiochemical outcome that they do. Right, there was a steric issue with that, but even more importantly, there was an electronic issue where the pi electrons attract out here, being pulled away from the carbon that can stabilize the partial positive a little better, and then this arrow shouldn't start there. The electrons come in from the hydrogen to form the new CH bond there. We already also, though, talked about alkenes doing the same addition. If it happens to the alkyne, that's good. I want to do the addition of the hydrogen and the boron across here, but then what I want to happen is to replace the boron with an OH, so I can make this enol, and then that enol can tautomerize into an aldehyde. I don't want the alkene to then react again. And that will give me something else altogether. So if I'm trying to make a CO double bond here, I need the hydroboration to occur only once. Only one hydrogen and boron adding across that pi bond, not two. So how can we avoid the second BH3 coming in here and adding again once one has already added? Well, the solution that chemists came up with for that problem is to, instead of having hydrogens here, I'll replace these with big bulky R groups. Big R groups that take up a lot of space. And that will block out the second one from coming in, so that this molecule will form and remain in solution until the boron is replaced with an OH, and then the enol can tautomerize to the aldehyde. So here are a couple of the most popular borane reagents that are used for this reaction in place of BH3. So we're replacing the BH3 with BHR2. And we got these big bulky R groups here, or BHR2. In this case, the two R groups are really part of one bicyclic system, but a very bulky group of atoms. And the idea there is when the BH3 adds across to create this alkene, the bicyclic system, or the two bulky R groups, will block out another BH thing from coming in. Right? So we won't even have BH3 in this. We'll have maybe this BH with these big bulky R groups. And so if one adds with the R groups on there, the other one's really going to have a hard time coming in here, because its bulky R groups will bump into the other one's bulky R groups, and it won't be able to get close enough due to sterics to do a second addition, which is what we want. We don't want two BH bonds to add across both pi bonds. We only want one BH to add across one pi bond. Then we want to replace that carbon boron with carbon oxygen, and then let the base catalyze the enol being tautomerized to produce the ketone or aldehyde that is the desired product. And so if you ever see these terms for these reagents, or even just 9-BPM, that's what you want to recognize. Those reagents will cause an anti-Markovnikov hydration across an alkyne, and then the resulting enol will tautomerize to a carbonyl or a CO double bond. Right, so let's just apply that here. So here's I see this bulky borane reagent. Got the boron hydrogen bond, it's going to add across here. The boron is going to add to the end. The hydrogen add here. Then the boron is going to be replaced with OH in the second step. So that's going to give me an alkene. The hydrogen here, the boron on the same side, because it has to add syn since they're adding at the same time across that pi bond. That's going to be replaced with an OH using the OH. And then the NOH is going to deprotonate this to create an enolate. And then that's going to rearrange through tautomerization to produce a CO double bond. So ultimately, this reaction does not change the number of carbons. It converts an alkyne into a CO double bond by doing an addition reaction and then a rearrangement. So I would expect you to be able to, given an alkyne, predict the correct products from this reaction, or given the product, be able to determine which alkyne and which set of reagents I need. So if I want to make a CO double bond here, I probably want to, since this reaction doesn't change the number of carbons, I want to keep track of how many carbons I have. So I'd still keep 7 carbons. The oxygen is going to be added across what would have been an alkyne. So I could imagine having the alkyne on this side or on the other side. If I put it here, that's going to be too many bonds, right? I can't have 5 bonds on this carbon. So my only option is to put the alkyne here. And that doesn't look too good because this bond should be linear. So really what this should look like is this. So I could use this set of reagents, or alternatively I could go with a 9-BBN. And then in the second step, the peroxide and the NaOH. That would first add the boron and the hydrogen across the pi bond. Then the boron would be replaced by an oxygen. But that would give me the wrong regiochemical outcome. Right? So I have to be careful. There's two ways to convert an alkyne into a CO double bond. And I have to decide which to use based on Markovnikov versus anti-Markovnikov. So I know this set of conditions will do anti-Markovnikov. It'll add the hydrogen to the more sterically hindered site, and because the partial positive will form there, and the boron to the other site. And then when the boron's replaced with an oxygen, I'll have the oxygen on the wrong carbon. If I want the oxygen on the second carbon, I need a different set of conditions. So that's where I use the H2SO4 and water and mercury ions. That set of conditions will give me the Markovnikov rather than the anti-Markovnikov that this set of conditions would use. So instead of the boron adding here and the hydrogen adding here, with this set of conditions, the pi bond picks up a hydrogen and the mercury stabilizes the positive charge that would form. And then water comes in to that carbon. So since it's the second carbon in that water will attack, that's the carbon where the oxygen of that water ends up remaining after it's deprotonated a couple times. And so eventually, initially, that will produce an enol, and then the enol will tautomerize into the ketone. So it's a bit tricky. You have to think about regiochemical issues. You have to recognize that the tautomerization is going to occur, and that initially this set of conditions will first produce the enol, and that's part of what you need to occur to get the CO double bond to exist on the correct carbon. So just make sure you're aware of which set of conditions you need to produce which regiochemical outcome with the CO double bond in the correct position. And that is what the next set of quiz questions were about. So if I want to synthesize a ketone from an addition reaction, any kind of R group bonded to a triple bond, if I have a hydrogen here, then I have to be careful. If I have R groups on either side of my triple bond, either set of conditions will produce a ketone. Right? So with the terminal alkyne, I can only use the Markovnikov hydration conditions because I need Markovnikov hydration conditions specifically to produce the alkene with the OH in the correct position that will then tautomerize to produce the ketone where I've got two R groups here. If I already have two R groups on either side of the alkene, I can use this set of conditions, or I can use the borane reagent. So like 9BBN followed by hydrogen peroxide and NaOH. Because now I don't have a Markovnikov or anti-Markovnikov option. Neither carbon of the triple bond has a hydrogen, so I could end up with the oxygen, well, initially the boron on either side, and then that would be replaced by oxygen on either side. So that would be a situation where if these two R groups are different, it'd be very difficult to control where the CO double bond forms. So I could have the OH form here, which would give, if the two R groups were different, it would give me the CO double bond there. Or I could also get the CO double bond forming on the other carbon. if I have an internal alkyne, there's no way for these reagents to differentiate between which carbon the oxygen adds to and which carbon the hydrogen adds to, because there's no Markovnikov situation unless one of the carbons has more hydrogens to begin with than the other. So if I want to form a ketone, there's a few different ways that I can do that. I can start with an internal alkyne and use either set of reagents. I'll get a mixture of ketones if the two R groups are not identical. And so then I'd have to separate those somehow. If I have a terminal alkyne, I definitely need the Markovnikov addition reagents to put the OH group in the Markovnikov position, and then when that tautomerizes to the CO double bond, it'll be a ketone because there will be R groups on either side. One of the R groups would be a methyl, but that's still an R group. So that's a ketone. If I want to make an aldehyde from addition reaction, there's really only one way to do that. I've got to start with a terminal alkyne, and I have to use anti-Markovnikov conditions. So either the diisoamyl borane or the 9-BBN. I like that one because it's easier to remember. And it also takes less time to write. And the second step's always going to be NaOH and hydrogen peroxide in any of these borane hydroboration addition reactions. But it's going to give me anti-Markovnikov. So the hydrogen adds to the side where there were fewer hydrogens, and the OH adds to the side where there were more hydrogens, and then that tautomerizes, and when it does, it gives me the aldehyde. Same number of carbons throughout, just adding hydrogen and an OH across a double bond with the correct regiochemical outcome based on the conditions we're using, and then the CC double bond becomes a CO double bond, and this hydrogen migrates over here through one of the two mechanisms we talked about. And if I have base specifically, just to maybe reiterate that mechanism, the OH minus, pick off this proton, these electrons would stay behind on the oxygen, or we could imagine them swinging in and going to the carbon, so there'd be resonance there. That would produce this. I drew that terribly. One more space and we'll redraw that. Right, so I just wanted to point out how that tautomerization works again really quickly. So the OH minus picks proton, these electrons would stay behind. Give me a negative, and then a water would be a proton donor for the next step. So these electrons will swing in and pick up a proton from water. And that would give me the CO double bond on the end of the chain, making that an aldehyde. Alright, so then the next reaction that we're going to look at in regards to alkynes is the halogenation. We said we can do a halogenation of an alkene. Right, so again, this is the same type of reaction. I get anti-addition, not necessarily anti-Markovnikov, because I'm not adding a hydrogen to either side. So the Markovnikov rule is not really anything to consider here. But the two bromines have to add anti to one another because the first one forms a three-membered ring and the other one has to attack that. We're going to get a similar situation here. Except when we look at the stereochemical evidence, we'll see there's some funny business going on here. But ultimately, in terms of the product production, this reaction works. Whether I'm using bromine or chlorine, it will add across the double bond. So I'll break one pi bond and add two of those, so Br2 or Cl2 across one pi bond, and then the other pi bond will break and I'll add a CO2 or Br2 across that pi bond. So I can get 4 halogens bonded to adjacent carbons if I start with an alkyne and add excess of the bromine or chlorine, because then it will react more than once and break both of the pi bonds. So if we look at this, how do we know that the mechanism is not the same as the one we looked at before with the 3-membered ring? Well, here's the evidence. This compound right here forms. Right, we said if the mechanism were the same as what we talked about for an alkene, if it's the same with an alkyne, then the pi electrons attack here, this electron swings back down, and this one leaves. And that would give me a 3-membered ring. And then if that happened, that 3-membered ring, if that happened, then the other X group that left would have to come in from the opposite side, right? That's why we always get anti-addition. If that 3-membered ring existed, it would be blocking out that side, and we would never be able to get both chlorines or bromines coming in on the same side. So the fact that this even forms, even though it's a minor product, the fact that it forms tells us at least some of the molecules are going through a different mechanism. Otherwise, we would only get anti. So this mechanism is actually still a bit of a mystery. So obviously we're not going to be able to tell you what it is or why. Ultimately though, if you use one equivalent, you get a mixture of products. If you use 2 equivalents or more, well then more X's would add across that pi bond. Both of these, I'll just ignore all that. Once I add 2 X's across, the other 2 would add as well across the other pi bond. So this other pi bond here would break, and in either case, I would get 4 halogens adding in total across both of the pi bonds. So be aware of that as a reaction as well. We talked about ozonolysis of alkenes. We can also do ozonolysis of alkynes. There's a slightly different outcome. In ozonolysis, if we had an alkene, we said the full thing breaks, the sigma and the pi. It breaks into 2 pieces. Each piece, the CO double bond becomes, the CC double bond becomes a CO double bond. So we get 2 different pieces. Each of the carbons, so we'll number these, carbons 2 and carbon 3. Each of the carbons that were involved in the pi bond now have new pi bonds, but they're doubly bonded to oxygen instead of carbon. Right? So ozonolysis for alkenes converts a CC double bond into CO double bonds and breaks the structure in 2. Same thing happens with alkynes, except now if I break the whole thing and separate it into 2 pieces, the carbons aren't just going to have a CO double bond, because they still need 3 more bonds to make up for the fact that they have 3 bonds breaking. And so the extra bond ends up connecting to another oxygen. So we're just fully oxidizing the carbons all the way up to the carboxylic acid. If one of those carbons is a terminal carbon, then it also has its CH bond broken and is fully oxidized into CO2, which would then escape and bubble out of the reaction. So just remember that if you have an alkyne and you do an ozonolysis reaction, you're still breaking the full triple bond. Each individual piece is still there. If there's a hydrogen, it's gone. If there's an R group, it's still there. But all the other bonds are then made with oxygens due to the extra unstable oxygen and O3 being introduced into the structure. So again, you don't have to know the mechanism for that in detail, but you do want to be familiar enough with the patterns of that reaction to be able to predict the outcome. Right, so here's an example of that. So I want to do ozonolysis on this alkyne. Just count the carbons to make sure I don't lose any. So I'm noticing that this is symmetrical. So I'm just going to number these with the same numbers. And recognize that the ozone is going to split this right down the middle, right down the alkyne. And so what's going to be formed here is the same R group bonded to carbon 1. And instead of having the 3 bonds to the other carbon 1, it's now going to have a COOH. So this is a convenient way of actually forming carboxylic acids. The downside of this reaction, and why it's not used very often, is it breaks your molecule down into a smaller molecule. Normally, the smaller molecules are cheaper and easier to buy from chemical companies than larger, more complex molecules. So most of the time, what organic chemists want to do is to take small molecules and build them up into larger molecules. Occasionally, though, it might be more convenient, creating a shorter synthetic route somehow to use an ozonolysis reaction. So you want to at least know how that reaction will affect the structure and what the products will look like. So I would actually form 2 of these since I'm breaking it and each half is the same. For each half, carbon 1 would end up as a carboxylic acid. Alright, so then the last type of reaction we're going to look at for alkynes, which is unique to alkynes and doesn't really relate to anything we've talked about for other molecules, is the possibility of an alkyne reacting as a nucleophile. So as we said when we first started talking about alkynes on Tuesday, that if I have a terminal alkyne, it is a very weak acid, but it's not nearly as weak as an alkane or as an alkene. These hydrogens are almost impossible to remove because the negative charge that would result on the carbon is extremely unstable. But the hydrogen on a sp hybridized carbon that's involved in a triple bond can be picked off by a base because the negative charge is stabilized fairly well in a more compact orbital. And we said the base to do that is NH2 minus. Because NH3 has a much higher pKa value than the alkyne, and there's about 13 pKa units difference, this reaction will favor the product sides by about a ratio of 10 to the 13th to 1. So this base is definitely strong enough to quantitatively convert every molecule of this, for the most part, into a nice looking nucleophile. Why is there the pKa difference? Because if NH3 gives up a proton, it forms a really unstable negative charge compared to the alkyne giving up a proton, because that negative charge is in a more compact orbital versus the other one. So this was the exception we had to learn in the beginning of the semester, because now it's actually relevant to these reactions that we want to look at. So if I want to convert a terminal alkyne into an alkynide ion with a full negative charge, so it can act as a nucleophile and bond to something new and increase the complexity of my molecule, NH2 is the base I want to use. Often that comes with the sodium counterion, so you might see NaNH2. Then once the alkyne has been deprotonated, and now it's an alkynide, it can attack an electrophilic site, push out a leaving group, and now I can make a larger molecule. So this is a really nice reaction where I can take a structure that has only so many carbons and increase the number of carbons in my chain. Start to build up the complexity of the structure little by little. So it's a two-step process overall. I'm first using the Na, which is just a spectator ion, with NH2 minus, and then H2 minus just simply does a proton transfer to create a negative charge here. Then that negative charge will act as a nucleophile and attack here and push out the iodide. So the limitation here is the electrophile that my alkynide is going to attack has to be primary. It won't work with secondary or tertiary alkyl halides due to sterics. If I did have my alkynide and I react it with a primary alkyl halide, it'll attack and do an SN2 most of the time. If I try to react it with a secondary alkyl halide or a tertiary alkyl halide, well then the sterics is going to preclude the direct attack at the electrophilic site. It's going to make the SN2 reaction too sterically hindered to work. So whatever our group this is, it's probably too big, even if it's just a methyl or a hydrogen. It's probably too big to allow this to make it in there when I've got other R groups in the way, especially if it's tertiary. It's definitely not going to work on a tertiary carbon. So instead, what would happen? Well, I would end up with elimination. And that's because it's also a base. Right? So it's a good nucleophile because it can attack here and push out a leaving group. But if there's too much sterics, instead of attacking directly at the electrophilic site, at the alpha carbon, it would instead come here to this beta carbon and just push out the leaving group through an E2 elimination. So that would defeat the purpose, right? I'm trying to build up the complexity of my carbon-carbon skeleton, so I want to make this new carbon-carbon bond here, so it'll only work in this synthetic route if I have a primary carbon that the nucleophile is going to attack. Otherwise, it would act as a base and go for a beta hydrogen. So here's one way I can use this reaction. If I just have acetylene, I can do it in a multi-step process. I can have the NH2 first pick up a proton. I can have the resulting negative charge here and push out the iodine and get that alkyl group connected to one of my two carbons. Symmetrical, doesn't matter which one I draw it on. Once that's connected, I can add another set of NaNH2, do another deprotonation, create another negative charge, and then have that push out an iodide and put the methyl group on the other side. So I can add really whatever primary R groups I want here. They have to be primary for the reasons we just mentioned on the last slide. But I can put whatever primary R groups here I want. I can't put them on both at the same time, which is what we're doing now. This will not work because I can't form two negatives on the same structure. It's too unstable. I have to do it one at a time. I've got to remove one proton and create one negative at a time. Two negatives on the adjacent carbons, they're like repelling one another too much. It's like really unstable. So I have to make one at a time and then have that attack a primary alkyl group with a leaving group. Then once that happens, then I can add another shot of the base to make the other carbon negative and attack the other alkyl group and push out a leaving group. I have to do it in sequence. I can't do it all at once. Alright, so one other issue that you might deal with is the reverse of some of these reactions we've already seen. So we now know how to convert an alkyne into an alkane using hydrogen and a metal catalyst. We can also convert the alkyne into an alkene depending on whether we want cis addition or whether we want trans addition. What if we want to do the opposite? What if we want to convert an alkane into an alkene? Or an alkene into an alkyne? How do we do that? So let's talk about that briefly. We know if we want to convert an alkene into an alkyne, what we need to do is first an addition across the alkene to get a dihalide. Then we can do the elimination E2 reaction on both halides, right? So we talked about this at the beginning today. We said if we have two halogens, whether they're on the same carbon or on adjacent carbons, there's a there's a possibility for this strong base to pick off a proton due to the E2, another molecule of the base, so we need excess of this. It would pick off the other proton, push electrons in, push the other leaving group out to another E2. And then the NH2 would pick off a proton and create a negative charge there, and then the water would be used to put that proton back on. So if I want to make an alkyne, I need a dihalide. If I'm starting with an alkene, I can make a dihalide from an alkene using Br2, or, well, Br2, Cl2 would also work, but Br2 works a little bit better. So that's how to convert an alkene into an alkyne. How do I make an alkane into an alkene? Well, that's something that we're going to see how to do in detail next semester, chapter 11. That would be explaining how to get a halogen to replace a hydrogen. So far, we've only seen substitution reactions where a nucleophile replaces a leaving group. If this hydrogen is a terrible leaving group, right? It can't leave with electrons and allow some nucleophile to come in and replace it, because it would be very unstable with a negative charge. So we're not talking about any of the reactions we've already talked about here. In chapter 11, we're going to see a different free radical mechanism that will allow hydrogen to be replaced by a halogen. So now, once we learn how to do that, we'll be able to use alkanes, convert them into alkyl halides, and then set up, for this step here, a strong base like an NH2 minus or terp butoxide or something like that to pick off this beta proton and eliminate the halide leaving group and make an alkene. So if I have an alkane, I can put a halogen on there, I can eliminate the halogen and make an alkene. Then I can take the alkene, put two more halogens on, eliminate both of those, and make the alkyne. So that general sequence you should be familiar enough with in case you need to use it to do some synthesis problem. So now we have almost every reaction we need to convert back and forth between any degree of unsaturation. From a fully saturated alkane to an alkene with 1 degree of unsaturation to an alkyne with 2 degrees of unsaturation. Why is water here? And that's, we already mentioned that, just to reiterate, it's because this NH2 minus, if we have excess of it, is going to pick up this proton. So the water is used as an acid to replace the proton. The proton comes from the water molecule. Alright, so let's just look at a couple examples. As I said last time, the idea behind synthesis is you have to be familiar with a lot of different reactions, and so you can kind of think in your mind which reactions are going to help me get from point A to point B, and that takes a lot of practice to get good at. It's not something that normally comes intuitively to students, so definitely practice as much synthesis in the textbooks as you can. You might have to deal with one synthesis problem on your exams the week after Thanksgiving, and you might have to deal with something like that on the final as well. So in a synthesis problem, the first thing I want to do is to count the number of carbons, because now that we have a reaction where we know how to connect two carbons together, the number of carbons in my chain might change, which is what's happening here. I'm going from a molecule with 5 carbons to a molecule and its other potential regiochemical product that now has 7 carbons. So how do I introduce 2 more carbons? Well, if I'm starting with an alkyne, I need to make it into a nucleophile. So there's a proton here at the moment. So the first thing I would do would be to add NaNH2. The negative charge of the NH2 would pick off that proton, and that would convert the structure into a nucleophile. So I still have 5 carbons. I want to put the next 2 carbons on. I need to add 2 more carbons. So the next step would involve putting two carbons with the leaving group, bromine or chlorine or something like that. This nucleophile would use its lone pair to attack here and push out the leaving group. And that would then add two carbons to the end of that chain. So then I have to figure out how to add across a triple bond in a way that will give me this particular stereochemical outcome. I'm trying to add a Br and an OH, and I want them to be anti with respect to one another. So how do I get anti-addition of Br and OH? Well, if I don't look carefully at where the hydrogens are, I might also overlook that I have to add two hydrogens across this double bond that are also anti with one another, with respect to one another. Right now, there's no hydrogens on either one of those carbons. So I have to add two hydrogens, and I have to add the bromine and the OH. So that's going to take a couple steps. So if I'm adding two hydrogens, I need conditions that will add two hydrogens across there, but still maintain the carbon skeleton in a way that will keep the pi bond so that the bromine and hydroxide can be added across the pi bond anti with respect to one another. So how do I convert this alkyne into this alkene so that the bromine and hydroxyl group can add across there in an anti fashion? Well, I need the cis. I need to make the alkyne into the cis alkene, because that will allow the reaction to produce the bromine and hydroxide across there by first making the three-membered ring either come up above or back behind, and then water would have to attack from the opposite side, one of those two carbons. Don't know which is why I'm getting two different regiochemical outcomes. But whichever one it attacked, it has to come in from the back side to push the bromine out the front, which is why if the bromine has a solid wedge, the OH has a dashed wedge. If the bromine started off coming in from behind with dash wedges, then the water would have to come in from the front. So the water would, or the OH would end up with a solid wedge, and the bromine would have a dash wedge, which is what I have over here. So in order to get the three-membered ring forming and the water coming in from the opposite side, I have to keep the carbon skeleton in this cis arrangement. So that requires me to use H2 and the Lindlar catalyst to go from the alkyne to the cis alkene, and then Br2 and water to add the Br three-membered ring, and then have water attack it, which would eventually be deprotonated to produce the OH and bromine anti to one another across what was the cis alkene. So that's a four-step synthesis I'd have to get through there. Any questions about that one? Alright, let's look at the second one here. Probably should have put these on different slides so I have more space, but didn't do that. So here we are. We count these carbons again. So I'm starting with 6 carbons, and I need to add 7, 8, 9. I need to add 4 more carbons. So that's my priority. I probably want to think about how to do that first. Right now I've got an alkene, and there are hydrogens here, here, and here. So I can't add more carbons to the chain until I make an alkyne. Right? We said once I have an alkyne, I can deprotonate that and make it into a nucleophile, and then have it attack another carbon and push out a leaving group. And that's how I add more carbons to the end of my chain. So first thing I have to do is make this alkene into an alkyne. So what I'm going to do first is to add Br2. And I'm going to do that in carbon tetrachloride to avoid any water coming in during the mechanism and creating the halohydrogen we saw last time. So the Br2 is going to add across the pi bond, and it's going to create this structure here, where I'll have a Br here and a Br here. And then I want to create the alkyne, so I'm going to use excess NaNH2. That's going to pick off the hydrogens that are beta to 1 bromine and push that out and make an alkene. It's going to pick off the hydrogen that's anti-periplanar and beta to the other bromine to make the alkyne. And then it's going to pick off the last hydrogen, because I'm using excess of that and it's very negative and unstable and it needs to pick up as many hydrogens as it can. The last hydrogen is going to create that alkyne as a nucleophile. So that all is going to do 2 eliminations and a deprotonation or proton transfer, and it's going to look like this. So then I just need to add these 4 other carbons, and since the carbon I want to add directly to the carbon that's negative, which is currently carbon 6, is primary. So I would just add the leaving group, bromide hydrochloride. This would come in, push out the leaving group, and that would connect carbon 6 with carbon 7, and that would give me the product that I'm interested in. So that one was a 3-step synthesis. And then the last synthesis was the last quiz question. So what I'm noticing here, as well as the last 2 examples, is a change in the number of carbons. So first thing I want to do is make my alkene into an alkyne so I can add these last 2 carbons to the chain. So I would first start with a Br2, just like we did in the last example. And I would put that in carbon tetrachloride. That would give me anti-addition of Br2 across the double bond. Then in the second step, I'm going to use excess NaNH2, just like we did in the last example. So this single bond would rotate so that this hydrogen would become anti-periplanar to this bromine. They would be eliminated. And then this hydrogen here would have to rotate so it becomes anti-periplanar to that bromine. They would be eliminated. And then the other hydrogen here would be picked off by the third molecule of NH2 minus, and that would leave behind an alkyne with a negative charge. Same number of carbons, still have 4 carbons here. 1, 2, 3, 4. I need to add 2 more carbons to my chain. So the next thing I'm going to use is a 2 carbon with the leaving group. That should attack, push out the leaving group, and now these last 2 carbons are now on my chain. I have a 6 carbon molecule with an internal alkyne. Now I see it's symmetrical. I have an ethyl group on either side of the alkyne. So whichever of these 2 carbons becomes the CO double bond, doesn't really matter which. If I put the CO double bond on carbon 4 instead of carbon 3, well, these 2 are the same structure. I just flip this over a couple times like a pancake and it'll lie directly on the other one. So in this case, since I have a symmetrical structure, there's obviously no way to control which carbon an oxygen might add to and which carbon a hydrogen might add to. But what I'm noticing here is I'm trying to convert an alkyne into a CO double bond. So there are 2 different ways I can do that. One is doing a Markovnikov hydration. But since there is no Markovnikov or anti-Markovnikov possibility, since it's a symmetrical alkyne, it doesn't matter whether I use Markovnikov conditions or whether I use anti-Markovnikov conditions. So I could use 9 BVN followed by hydrogen peroxide and NaOH. Either of those reaction conditions will put an OH on one of these carbons and a hydrogen on the other. There's no way to control which because it's a symmetrical structure. Whichever carbon the OH goes to is going to end up tautomerizing into a CO double bond. It doesn't matter which hydrogen or which carbon that occurs on because I get the same product either way. So for step 4, I could put the in for my answer, or I could put that set of conditions in. Any questions about that one? All right, so there's the bullet points for today's content. Day 26 and 27 primarily are what you're going to be tested on the week after Thanksgiving. So practice up. Let me know if you have questions about any of this practice. In the meantime, next week, I won't see any of you except the Monday students in lab. Right, so the Tuesday and Wednesday students have already taken exam 12. The Thursday students are taking it tonight. The Monday students are taking exam 12 this coming Monday before Thanksgiving. And then Tuesday of next week, during our normal lecture time, since we've already gotten through all of the new lecture content, we'll just have an informal review. So as you're preparing for exam 13 and now hopefully also thinking about preparing for the final exam, please look at examples and come with some questions or examples to work out on Tuesday of next week. So Tuesday of next week, I will be at the computer at 1 p.m. at the normal time to review with whoever wants to come on. If you don't have any questions, I'll try to come up with some. But you should have plenty to ask about as you're preparing for exam 13 and the final exam. Obviously, next Thursday, we won't have any review or lecture. That'll be Thanksgiving. Obviously, we're not doing anything together that day. And then the week after Thanksgiving, we'll just be finishing up lab and taking exam 13 in your lab sections. But the Tuesday and Thursday after Thanksgiving, during our normal lecture time at 1 p.m. on Tuesday and Thursday of the week after Thanksgiving, we will be reviewing for the comprehensive final exam, and there will be some questions that I'll be presenting to you here over Discord. And in your lab groups, I'll be looking for you each to be contributing there, and whoever is on the feed that day and answering questions within your lab groups, if you're answering those correctly, you'll be able to earn some bonus points. I'll be keeping track of that. And then I'll add those points on to probably your exam 13. But they'll be course points, so whichever assignment I add them to, it's going to affect your grade the same way either way, so it doesn't really matter where I put them, but I do want to put them on. I'll put them on as soon as I can after those review sessions. So we'll be reviewing Tuesday at 1 p.m. and Thursday at 1 p.m. the week after Thanksgiving. So if you come to both of those, you could potentially earn up to 20 or 30 or even maybe even up to 40 bonus points, depending on how many of those questions we can get through in those roughly 4 hours combined review time. So that is the plan. If you have any questions about anything or comments of any kind, please